Hello everyone. So I'm Véronique Gendner. I've done data processing, worked on the representation of information for data modeling and visualizations. Graph has interested me 20 years ago when I was doing NLP with formal linguistics, then for structuring documentation, and 5 years ago I've specialized on graph technologies, databases and visualization tools. I'm currently looking into the possibilities of GraphRag to access private or specific documentation. What we'll be looking into now is what can we do when our Cypher query takes too long. Cypher, the label property graph database query language, is a declarative language. A declarative language means you describe what you want to get, not how to get it. As Cypher is also a visual language based on ASCII art, you use rounded and square parentheses to write the pattern of nodes, relations, and properties that you are searching for in the database. That is basically you draw a graph pattern and the database engine has to figure by itself how to get it for you. This is very easy and comfortable at first because you can get results without minding how things work under the hood until one day you write a query that does not terminate and you don't know what to do. As a matter of fact, searching a graph is a hard thing to do. Searching in a graph means traversing it, and this is hard for several reasons. First, there's no straightforward place to start. Finding where to start is the first choice that needs to be made. As a graph database is a general graph, not a tree, it possibly has cycles. Determining the best way to traverse the graph, not missing items and not getting trapped in cycle is not straightforward either. More choices need to be made to find a balanced compromise between processing time, memory, and disk space usage. The most common answer to a query tuning question is it depends, which can be frustrating. But indeed, improving a query does depend on a lot of things, including the shape of the specific graph that you're searching. This often makes a specific answer difficult to formulate without getting into a lot of details. So do not expect rock-solid truth because they're pretty impossible to formulate. This presentation is about useful guidelines to different aspects you should be aware of in order to optimize the way you write Cypher queries, starting with key principles of Cypher execution. We'll get into how the Cypher query planner works, see examples and hints, and briefly go through some of the other levels than the query itself that also impact processing time. On the last slide, together with resources to go further, you will find the link to a post where the slides with the slides with detailed comments and the replay of the representation when they're available. So don't worry if it's a little fast, you can get an overview now and later go back to the slides at a comfortable speed. The Cypher query processing is in 3 phases. First, a passing rewriting phase that will, for example, rewrite the different variant of a node property match that can be either in the node or after the where keyword. The second phase is the part we're mostly interested in today, and that is the production of a logical plan, sometimes also called execution plan. The query planner, sometimes called query optimizer, is in charge of building this execution plan. The third phase is the execution by the database kernel of the operators produced by the query planner, but this is at a lower level than what we need to know for general optimization of queries. So let's first concentrate on the query planner and the execution plan it produces. The query planner is the part of the database engine that determines the most efficient way to execute query. It does so according to the current state of the database, that is based on counts of certain DB items. We'll get back to those statistics. Due to the nature of graphs, for any given Cypher query, there is likely a number of execution plan candidates that each solve the query in a different way. The planner determines which plan has the lowest estimated execution cost. What the planner takes into account are number of rows, number of database hits. Sometimes it uses heuristics to avoid certain operators, like more memory costly ones, or to favor others, for example, to leverage the use of indexes. This is a general idea. Also be aware that in some specific cases, a higher number of rows or database can be quicker if it uses a less costly kind of database list. But generally speaking, reducing query processing times means reducing the number of rows and the number of hits. The statistics of the database used by the query planner include the following. If you want to check those of the current database you're running, you can call this db command, and it will return a JSON object that looks like the excerpt you can see in the gray area of the slide. It includes counts about nodes, total number, and number by label, counts about relationship by type, but also by type together with the starting label, and by type together with the ending label. The query planner also uses counts concerning indexes, how many values, and estimate of unique values to know about the selectivity of the index and choose the most appropriate accordingly. The planner also knows about constraints that exist in the database. So the first thing we want to minimize is the number of rows. Then what are rows? Let's take the sandbox movie database that you can try for yourself here. It has two node labels, movies and person. And for example, the matrix has 5 actors related and 2 directors. If you want to get the list of actors and the list of directors of the movie, you might write a query that matches the movie, then grabs person nodes related to the movie node and other person that are connected to the movie with the acted in relationship. But then you will get a list with 5 times the name of each director and 2 times the name of each actors. And this is because of how rows are produced during the query processing. We'll see this in a minute, but let's first see what the query planner important phases are. This is a very important part to figure out. As an example, let's take the simpler query that produces the title of the Matrix movie and just the list of its directors. The first thing the planner does is find anchor nodes, that is, nodes from which it makes sense to start the search. In this case, we only get 1 anchor node, but in more complex database or queries, there can be several anchor nodes. Then comes the expand phase that consists in following relationships as specified in the Cypher pattern. So in this case, it follows directed relationships, which results in 2 rows, 1 for each director related to the movie. In this, the third phase is filtering rows, typically to abandon rows that don't match a label or a property that is specified in the query. In this case, the filtering phase has no effect because in this database, when you expand from this movie with the directed relationship, you only get node labeled with person. If you had nodes with other labels related to the movie with the same type of relationship, the expand phase here would have grabbed them, then the number of rows would have been reduced by the filtering phase. Finally, collect is an aggregation function, which makes the title property of the movie node is the implicit key, and directors are aggregated for each value of this key, typically here 1. And this results in the matrix with the list of the 2 directors. Now let's get back to our query to get the list of directors together with the list of actors. If we apply the tree phase we've just seen, the first match produces 1 row. As we've just seen, the second match produces 2 rows along the directed relationship. Now we could think that the third match will produce 5 rows, 1 for each actor. It does, but match clauses are not independent. We still have the 2 rows from the second match. So the 5 rows of the third match are produced for each rows of the second match here. This is why in the output list, we get 5 rows for the first director, 1 for each actors, and the same for the second director, and twice the name of each actors, 1 for each director. This is why to get the expected result, you need to add distinct in the collect function. But the main point here is to give you a sense of how rows are created, because reducing the number of produced rows is an important lever to reduce query processing time. Another important lever to reduce processing time is reducing the number of database hits. A database hit is an abstract unit of storage engine work, such as retrieving or updating data. Action that triggers database hits are, for example, create or delete, or reading actions like getting the label of a node, getting a property of a node or a relation, or finding a node or relation through an index. Those are examples of database hits. An important piece of information for tuning a query is the logical plan produced by the query planner. To see it, there are two keywords you can prepend to your query: explain and profile. The main difference between the two is that explain does not run the query, profile does. So if the query has create, delete, set, or remove clauses, you might not want to use profile. Also, if the query takes a very long time to run, explain might be more helpful. But explain only gives number of row estimates. Since profile runs the query, it provides actual number of rows and number of database hits. Shown estimates are based on the statistic we just talked about, so don't be surprised if you see an estimate of 0 or 10 rows when you know there is, say, 5 nodes that should be resulting in 5 rows. This is because estimates are rounded statistics. The output of explain and profile come in two different forms: a visual diagram like you can see here, or a text version that we'll see example of in a minute. Here you can download the output, and the first hint is if you ask a question about how to tune a query, send the explain or profile output, because it gives lots of useful information needed to analyze the situation. If you run the following query in the Neo4j workspace, the top of the result windows will look like this. To the left, you have 3 tabs. If we were running nodes and if we were returning nodes and relationship, we will have an extra graph tab to show the outputted graph. Here we return a property, so the output is a table that you can see on the table tab. But what we're interested in here is the plan tab that only shows when you prepend, explain, or profile to your query, and that displays the logical plan produced by the query planner. To the right of the screen, you have those 2 buttons to select between the text or the image, the form of the plan. The 2 forms provide the same information, just in a different way. The text form is what you also get if you run the Cypher shell, and the image form you also get with the Neo4j desktop version. What you can see here are profile outputs. Explain outputs are similar, but with less information, since explain does not run the query and therefore only provides estimates. An important difference between the text and the image form is that they read in the opposite way. To read the plan in a sequential order, you need to read the text version from bottom up. The result is indeed at the top when it's at the bottom on the image version. One important piece of information provided by the plan are which of the query planner operators are used. The root operator provides the result. It is the last node of a decision tree that starts at leaf operators, and leaf operator search for anchor node, as we've seen. It's the first important phase of the query processing. So the query planner translates a Cypher query into a sequence of operators that will be executed by Cypher runtime. Let's now look at what query planner operators are. With the profile output of the query, we have already looked into to figure out what rows are. Leaf operators from initial search to determine So yes, sorry, some red thing appeared on my screen. Leaf operators perform initial search to determine starting point for the graph traversal. In this case, a node index seek operator that you can find at the bottom of the text output of profile. The second operator that applies is an expand operator. As we've seen, it expands along the directed relationship that is specified in the query. Then the filter operator that has no effect in this case. And there is a cache operator because the name property has been put to property cache. The planner uses different kinds of cache, and I'll say a word about that later. Then another expand operator along the acted-in relationship, a filter operator that has no effect for the same reason as previously. And before returning the result, we have an aggregation operator with a movie title as an implicit key, and that collects distinct directors and distinct actors. Note that this is a very simple example. Oftentimes, the planner starts with several leaf operators, then decides which branch is best or joins several branches to get the results. There's a kind of operator that you need to watch out for, and they are eager operators. For the sake of time, I will not go into details, but in short, eager operators slow query processing and are more memory hungry, so the goal is to use as few eager operators as possible. I also have to skip the walkthrough of the list of operators. You can find them in the documentation. And because the list is pretty long, I've put them in a spreadsheet that is also linked on the slide to make it easier to browse the list with search and filtering to figure what they do by comparing similar operators. Before getting into some example, I must confess something. That is, I probably waited too long before taking the time to understand how the query planner and operators work. In my defense, there were not many resources on the subject when I started writing Cypher, but I'm telling you now, taking this time really is worth the investment. After the simple example we are seeing today, I do recommend practicing, including on a real-life-sized database. This being said, I also think there's a balance to find between the amount of time you spend optimizing and the amount of machine time you earn. When your database is in the range of millions and you do not have real-time constraints, there's a lot you can get away with because the planner will take care of it. And I don't see the point spending seconds or minutes of human time to earn milliseconds of machine time. Also, I do recommend not to kill human readabilities of queries for overkill performances. I thought this presentation is the one I wish I'd find when I started. First, to understand how the Cypher query planner works and how to read and explain profile output, as we've just seen. Also, as a sort of checklist of things you can look into both at the time when you need tweaking a query that takes too long and when planning your training. Let's get back to our movie directors, actors example, because one thing you need to know is that different syntax of queries can result in the exact same plan. You can write the 3 matches like we've seen so far, or just one match with the movie in the middle and actors hooked on one side, directors on the other side. And this will give you the exact same plan, because no matter how you write a query, the planner goes by the same phase we've talked about. It figures that given the query and the database counts, the movie node seems like the best choice to anchor the search, then expands, filters, and collects. When a node or a relation is not reused in the pattern, you do not need to give it an explicit variable name. In this case, the planner assigns the name anon plus an incremental number, like here. You can see, for example, that anon 0 is the acted-in relation, but what is anon 1? It can be, when you have a larger plan that you need to scroll up and down, or you have lots of variables, it can be very helpful to give nodes and relations an explicit name, like here, to help read the plan. Now, let's say we want the list of directors for each movie, and since we've built the database, we know that the directed relation only exists between a movie and a person. We might be tempted to write the query like this without node labels. I know it because I've done it, but it's a very bad idea for several reasons. First, because if you do not specify a label, the only choice the planner has to find anchor nodes is to use all node scan operator. In this case, we can get away with it because it's a toy database with 171 nodes, but in a real-life database, you do not want the first operator to generate as many rows as there are nodes in the database. So we should really use at least one label so the planner can use an index if there's one on the property you're filtering with, or worst case scenario, if there's no index, it will use a node by label operator that will at least reduce anchor nodes to the nodes with the specified label before filtering down according to the property. The second reason it's a good idea to specify labels is for readability of your queries. And the third reason is that you might keep the query to run later, but in the meantime, your database might have gotten more complex, and you might then have other labels around the relationship you're matching. If you rerun that query that was working fine with no label back then, you'll get into trouble when the database gets more complex. One general use you can keep in mind is the sooner you collect or filter, the less rows you get. Hence, you reduce the query processing time. For example, with our now well-known matrix actors directors query, remember it first expanded to 2 rows, one for each director, and then this number of rows gets multiplied by the number of actors. If you move to the collect directors part up, you reduce 2 rows to 1, which on a real-size database can make a lot of difference since you reduce the first cardinality of rows that will be multiplied by the second cardinality. In summary, one important thing you should keep in mind when you want to reduce query processing time is to reduce the number of rows. As mentioned, in some cases, a higher number of rows can be quicker if it uses less costly kind of database hits, but the first move is to reduce number of rows. We've seen you can do that by specifying labels to avoid all node scan operators, use indexes, collect and filter data as early as possible. And there are more ways, some of them described in this insightful talk by Andrew Bowman. Just be aware that due to Cypher updates, some parts are outdated. Something we need to keep a close eye on are dense nodes. How is that? For example, this is a portion of the model used for the Graph Academy course. You have users and courses. Courses are made of up to 3 modules, and modules contains lesson. This user enrolls for courses, which is represented by an enrollment node. This is a portion of the database for a course made of 3 modules, each with 2 or 3 lessons, and user enrolled for the course. Now, the problem is that Neo4j most popular fundamental course has 40K enrollments. This is what is called a dense node. That is a node with a high degree, a lot of connection. This means that expanding from this course to the 4-course relation is very costly. Then how to avoid dense nodes? Well, the first way is to try and avoid them at modeling time, but as this example shows, it's not always possible. Not everything can be anticipated at modeling time. As I'm running short of time, I do not go into the details of how you can use an index hint to avoid it in this case, but you can find them in this article by Adam Cooley or in the slide that will be published. Besides reducing number of rows, you also want to reduce database hits. And although here there have been improvements in the most recent version of Neo4j, property access are costly. Here are some pointers to reduce the cost of property access. We've seen several uses of indexes. They are definitely a useful lever to look into for query processing time reduction. Now, what can we do? What can be done about relationship? For example, specify relation direction and type is one hint. Set an upper limit on variable length pattern is another hint. For more about that, I do recommend you watch the Michael Unger presentation. Since I have to wrap up, here are just pointers to 3 Cypher subjects that you should definitely look into because some of their use cuts down processing time. This is all about the query itself. Let me quickly mention other levels that have an impact on the query processing time. You need to be aware that several caches are involved in the different query processing phases. Sometimes simply rerunning the same query results in a significantly faster processing time. And to be honest, I'm still working on figuring out what is a consistent way to compare queries processing time in a way that properly takes into account the time difference due to the cache and not to the tuning of the query. So we've seen the Cypher. We've seen the Cypher query processing time depends on the architecture, that is the logic and statistic of the query planner, on the wisdom of Gandalf, this is your knowledge and practice, and it also depends on R2D2, that is the characteristic of the machine that runs the query. This is a whole subject to look into. Let me just share the typical memory configuration you can use if you're running Neo4j on a desktop, on the desktop version on a laptop. And lastly, modeling needs to be mentioned. That happens further upstream of the query, of course, but it's related. And in some cases, it's a good idea to leverage the flexibility of what DAFTAB is, for example, using a temporary label at import time. Okay, that was a lot for 30 minutes, but the purpose was to give an overview of landmarks that you can use to dig further. Here are resources to do so and online communities where you can ask questions. With that, thank you for your attention. I don't know if maybe we have a minute for question, if there are some.